Good afternoon, everyone. My name is Aninda Chatterjee, and I have Karthick Murugan along with me, and the two of us will be taking care of the technology session for the day. So the agenda for the day is pretty straightforward, but it should be a lot of fun. We have a lot of labs for you. So we're going to start with the spanning tree best practices, spanning tree features that you should implement which are good for your network, just good protective features which are very useful. We're going to move on to layer 2 loops, the symptoms that you should look for, how you can spot a layer 2 loop and troubleshoot it. We then move on to topology chain notifications, what they are, how do you identify them, and are they good, bad, how exactly would you work with them. We then move on to stacking and licensing, and then wrap up the session with the QOS basics. So without further ado, I'm going to start with the spanning tree. So spanning tree, the most important enhancements or features that were implemented are listed here. We're going to cover loop guard, root guard, BPDU guard, BPDU filter, and port fast. So let's start off with the loop guard and what exactly is loop guard used for. So loop guard is, as the name describes, right? Loop guard is used to prevent layer 2 loops in your network. The main intention behind that is if under certain conditions your layer 2 switched topology is might go under a loop and you might have a broadcast storm and all of that. Loop guard is intended to prevent that from happening by basically shutting down the interface which might lead to the loop. Right. So in your layer 2 switched network, there's something called as segments. And as an example, you can take a switch to a switch connected by an Ethernet link. That is one segment. Now, as per spanning tree requirements, we always should have one designated bridge, one designated port per segment. The designated port, as all of you might be aware, is responsible for sending out your spanning tree BPDUs. It will always be the designated port that is relaying your spanning tree BPDUs, and the other side is basically meant to receive and process them. So the failure conditions basically for a loop, the most common failure conditions arise out of the fact that you might have some sort of unidirectional problems in your segments where you're not able to process BPDUs or you're not able to receive BPDUs, or the other side, the designated port, is not able to send BPDUs to you. So in that situation, the bridge which is meant to receive BPDUs, it basically assumes that the designated bridge has been lost for that segment, and as per spanning tree requirements, there has to be at least one designated bridge per segment. So this bridge now starts to move itself to a designated bridge role. It moves its interface to a designated port, and suddenly you have a loop in your network, right? So loop guard basically is used to prevent such situations. So I'll explain this with an example. It's a very straightforward triangle topology. You have switch A, switch B, and switch C. Switch A on top is your root bridge for, let's say, VLAN 1. And you can see the port roles, I've mentioned them here in the diagram itself. Switch B's connection to switch A is the root port, switch C's connection to switch A is the root port, and switch C is blocking its interface towards switch B. So at this point, this is how spanning tree has converged, and at this stage you do not have a loop in your network, right? The BPDU flows are also given here in the diagram. Switch A, being the root, of course, has both its interfaces as designated ports. So now let's consider a situation where, for whatever reason, BPDUs are getting lost between switch B and switch C. So in transit, BPDUs are not reaching switch C. The reasons can vary. Switch B might not be able to generate these BPDUs. Switch C might not be able to receive these BPDUs, or it's just being lost on the wire. So because switch C is now no longer receiving BPDUs from switch B, it assumes that switch B, which was the designated bridge in this segment, has been lost to it, and it has to move itself to a designated bridge role. So it slowly starts converging and it starts moving its blocked port to a designated port. So now we arrive at a situation where the blocked port becomes a designated port and you no longer have any blocked port in your triangle topology. And this is a very, very clear loop in your network. And in this situation, if there's a single ARP or basically a single broadcast packet that is put into this topology, it will loop around forever and ever because, as you know, layer 2 broadcast packets, they don't have a time to live, so they never die. So the only way to overcome this situation and to sort of stabilize your network would be to shut down one of these links for quick recovery. So what LoopGuard does is, let's say you implemented on the blocked port. What LoopGuard will do is when switch C stops receiving those BPDUs and it attempts to move itself to that designated role, that's when LoopGuard kicks in, and LoopGuard will error disable the interface, putting it in a loop inconsistent state, and you no longer have a loop in your network. So you've lost one interface, but at least you don't have a loop in your network, which will cause a lot of mayhem instead. So these are the kind of situations that LoopGuard prevents and tries to maintain that stability in your network. There are several ways that you can configure LoopGuard. You can do it globally. This is using your spanning tree LoopGuard default command, or you can do it per interface using spanning tree guard loop command. Now, one of the really important questions to address and understand is which interfaces should have LoopGuard configured on it, right? Considering just this topology. So the most obvious answer that comes to mind is your blocked port, because those are the ports that will move immediately to forwarding to cause a loop. But something that a lot of us miss is that you need to have LoopGuard implemented on root ports as well. So just to generalize, LoopGuard has to be implemented on all non-designated interfaces. And the reason for that is, I'll just give you a small example. Let's take the segment between switch A and switch C. So you have switch A, which is sending BPDUs down to switch C. Switch C's interface to switch A is the root port. So let's take the event where BPDUs are not reaching switch C. So what switch C thinks is my root port has been lost. I no longer have an available path to the root. Now I do have an alternate port which can lead me to the root. So what C will do is it moves the previous root port to a designated port, and it moves the blocking port to a root port. And again, you have a loop in your network. So this is how a root port can also cause a loop in your network. This is why you implement LoopGuard both on root ports and blocking ports, more generally on all non-designated interfaces. And if you can just do a show spanning tree summary, that should tell you if LoopGuard has been enabled on your switch or not. And apart from LoopGuard, which is meant to prevent such unidirectional issues, you can also use UDLD, which is again a very good mechanism that can detect and basically error disable your interfaces if you have unidirectional problems, where one side is sending but the other side is not receiving. The second feature which I'm going to talk about is BPDU guard. And this is again a very good enhancement feature of spanning tree which should be implemented in your networks. BPDU guard is the entire purpose of BPDU guard is that you control your spanning tree domain, right? You're basically controlling the depth of your spanning tree domain. You're controlling how many switches can participate in your spanning tree domain. So the first main advantage of this is, let's take a situation where you have 6 or 7 switches, and let's say you have on the 6th or 7th switch you have a host connected to an interface. Now, what is stopping the user, the end user, from plugging his own switch into the network, maybe with a really low priority, and causing a massive reconvergence and basically taking over your entire spanning tree domain? So these are the kind of situations that BPDU guard prevents. You will basically error disable the interface if the interface ever sees a BPDU coming or ingressing into it. So the best way to implement this is simply use the default command. You can just enable it by default, and what that does is it is going to enable BPDU guard on all port-fast ports. And port-fast ports, as you know, should be configured basically going to your end users, workstations, servers, etc. So these devices are never expected to send BPDUs, and if they are, that is a problematic state. That is something we want to avoid, because we never want to process those BPDUs and learn their information. So we prevent that by using BPDU guard, and we error disable the interface if we get a BPDU on the interface. So next thing that I'll cover is root guard, which is again a very handy feature. Root guard is basically meant to protect your placement of the root bridge. So you're basically ensuring that if I have switch A configured as the root bridge for my domain, I want to make sure that switch A remains the root, and there's no other switch that plugs in, even though it might have superior information. I want to make sure that it cannot overcome switch A. I want to make sure switch A remains the root, right? And how you implement root guard is you want to protect the root by protecting your designated ports for segment. Designated ports are basically downstream ports which lead you away from the root, and that is what we want to protect. So root guard, there's no global command for root guard, it's a per port feature. So you have to implement this on a per port basis. So one thing to keep in mind is the placement of root guard has to be very strategic in your network. This is because we've seen failure conditions where let's consider a switch, and let's say that there was a failure condition in such a way that the switch lost its path to the root, or basically lost its knowledge of how to get to the root. When that happens and it no longer has any alternate ports that it can use to go to the root, it naturally declares itself as a root momentarily. Now what happens is, in that situation, root guard will kick in, and it starts protecting that newly formed root, which should really not be the root. So if you get a superior BPDU for reconvergence, we've seen issues where your reconvergence does not happen very well. So in that situation, you should have a very well-tested working scenario where you know how your placement of root guard can affect things. And a very common way to use this is when you're sort of interfacing with other customers, and you basically want to make sure that the root bridge is in your domain, and your customer cannot dictate or change how the root bridge placement is there in your topology. So the interfaces which face your customer, you can go ahead and configure root guard on that. So if your customer is doing some fancy things in his network and he wants to make his bridge or his switches the root bridge, when they try and send superior BPDU information to your domain, that will error disable the interface and prevent that from happening. So that's a handy way of using root guard in your topology. Coming to BPDU filter, that is something that TAC does not really recommend, because we've seen a lot of situations where BPDU filter has been used incorrectly, and that is a very, very dangerous thing to do, because what BPDU filter does is it very silently stops the transmit and the receipt of a BPDU. So if you have a BPDU filter or interface, let's say 1, that interface will not transmit any BPDUs. That interface will not process or receive any BPDUs that are ingressing into it. So it does not error disable the interface. Its functionality is very, very silent, and because of this, it's very easy to have a loop in your network when you have an incorrectly placed BPDU filter on an interface. So for TAC, BPDU filters are a strict no-no. We highly recommend that you do not use it, unless, of course, you have a very, very well specific and thought out reason for using BPDU filter in your layer 2 switched domain. From a feature perspective, the last thing that I want to cover is what is port fast and why is it important. So I think we all are aware of different spanning tree flavors. I'm not going to get into that at this point. But just to give you a rundown, you have your per VLAN spanning tree plus, which is PVST plus. Then you have your rapid PVST plus, and then you have MST, which is these are the spanning tree flavors that Cisco currently implements, right? So with PVST plus, you know that there is a certain delay before interfaces can actually start forwarding traffic, right? You have your listening and learning, which is your forwarding forward delay, and each of them are 15 seconds each. So if I have an interface which just comes up, it is not going to start forwarding traffic in the next second. It takes, at minimum, it is going to take 15 seconds of listening, 15 seconds of learning, and after that, it moves to forwarding, where actual data packets can traverse through it, or it can receive data packets. Now, when you have workstations and end hosts, servers which are connected to your switches, we don't want that delay. If the server comes up in 1 second, you want the server to start transmitting its packets in 1 second. So that is the main use of port fast. You want to overcome that initial workstation delay. You do not want that at all. So what port fast basically does is it will skip your 15 seconds, that's 30 seconds of listening and learning together, and it will directly put the interface in a forwarding state where it can actually start transmitting packets. So as a good practice, you should always implement port fast on end user workstation server facing ports. The other thing to sort of keep in mind is port fast affects topology changes as well. So I'll get into that feature of port fast when we're talking about topology changes. Now, the other thing that we've sort of heard quite often is considering the same topology I used earlier, which is your triangle topology, and let's say we have port fast implemented on every single interface, and we bring the switches up. A common misconception that we've heard is there will be a permanent loop in the network because port fast directly jumps to forwarding and it does not go through listening and learning. That assumption is incorrect because what happens is on a port fast interface, if you receive a BPDU, when a port fast port receives a BPDU, that interface will lose its port fast tag, and there's a handy command to look at that. I'll get into it on the next slide. But this is a very, very key thing to remember. If a port fast port receives a BPDU, that status is no longer there. Even if it stops receiving a BPDU, the status no longer remains. To get the port fast feature back onto the interface, you have to do a shut, no shut. So in the topology I was describing, even if you have port fast on all three switches on all interfaces, yes, there will be a loop, but the loop will be sub-second and it will not be there permanently. As soon as the BPDUs are received on the interface, they get processed and one of your interfaces will go into blocking, preventing the loop. So port fast can be implemented again either globally. If you implement it globally, it applies to all your access interfaces, and of course you always have the option of implementing it per port. So now the best way to look at whether a port is operational as port fast or not, you can do a show spanning tree interface port fast, and that will list out whether the interface is enabled or disabled for port fast. So the command here, I've listed that out for a trunked interface, which is why you see a bunch of VLANs. So I've gone ahead and done it for a single interface as well, and that's what you see here, right? I just used two switches, switch A and switch B. Switch A was the designated port, so switch A was supposed to send BPDUs to switch B. What I did was I put a BPDU filter on switch A. So switch B was no longer receiving anything. I enabled port fast. So at that stage, you can see that port fast was enabled for VLAN 1 on FA0/2. I then went ahead and disabled the BPDU filter. So now BPDUs are being transmitted to switch B. And I see as soon as I receive a BPDU, my port fast goes to disabled. So I am no longer operating as a port fast interface, right? So those are some of the really important spanning tree features which you absolutely must understand and implement in your network, because they're very key in troubleshooting and preventing a lot of instability, especially things like loop guard and BPDU guard. And So if you know, I think it's a good thing to do an audit, make sure you have such things in your layer 2 switch network, and if you don't, it'll be good as an engineer to recommend to your management that these are some things that you should have. So let's move on to a lab where I'm going to show you the main intention of this lab is to help you understand what are layer 2 loops, and more importantly, if you have a layer 2 loop in the network, how do you identify it? How can you say that I have a layer 2 loop in my network? What symptoms should you look for? And then of course, how do you troubleshoot it and how do you fix the problem? So this is the topology that we're going to work with. It's similar to the earlier one that we were looking at. You have 3 switches. It's a very simple topology. Switch A is my root of the network. Switch B, as you can see, the interface to switch A is a root port, and the other side is designated, and switch B is blocking its interface towards B, which is why there's no loop in this network. So just give me 1 quick minute. I'm going to bring up the switches, and we'll have a look at it live and see what's going on. All right. So I'm assuming everyone can see the switches at this point. Let me just bring up the consoles for this. So I have these 3 switches here. As you remember from the topology, I have switch A, which is in the middle, which is the root of my triangle topology. I have switch B, which is on the left. I have switch C, which is on the right. So let's just look at spanning tree for VLAN 1. So switch A says I'm the root bridge. So that's a given. We've identified and confirmed that. You can ensure that both its interfaces are designated forwarding. So when we go over to switch B, it says, so you can see here, FA02 is the connection that goes to switch A. That is a root port, and the other port is a designated port. So let's go over to switch C. Switch C, let's look at source CDP neighbors and see what's going on. So 2/0/3 is what goes to A, which is a root port right here, and 2/0/2, which goes to B, is alternate blocking, right? So at this point, spanning tree is converged, and there is no loop in the network. So what I'm going to do is I'm going to go over to switch B, and I will simulate a looped environment, right? So all I'm going to do is I'm going to put in BPDU filter, which should stop BPDU is being transmitted, and C should stop receiving these BPDUs, and you should see a loop form in your network. So let's do that now. So I've gone ahead and enabled BPDU filter on the interface, which is facing switch C. Of course, this is just for testing purposes, and this is just to help everyone understand. So please do not attempt anything like this in your production environment. So you see what's happening on switch C, right? This was the interface which was earlier alternate blocking. Now, as per PVST plus rules, I will wait for 20 seconds, which is my max age timer, and I will wait for 20 seconds to ensure that I'm not receiving a BPDU. Once 20 seconds expired, I attempt to move to a designated role. So that is what it is doing at this point. It moved to designated, and its status is listening. It went through learning, and now we can see it's gone to forwarding. So now the previously alternate port is now forwarding. There's nothing that is blocking in your topology. So this is a loop in your network. So now that you think you might have a loop in your network, the first and most obvious, a basic telltale sign that you should look for is MAC flaps, right? And I will explain a little more what MAC flaps are, but MAC flaps on some lower end switches, MAC flaps are basically enabled by default, and on some of the higher end switches, you have to sort of go in and enable MAC flaps, like the 6500 or the 4500. there's a command that you have to go in and enable MAC flaps, and I'll just show you the command here quickly. So it's basically MAC address table and notification, and then you do a MAC move. That will enable the command for the switch, and it starts logging if there are any MAC moves in your network. So I'm just going to do a show log because I've disabled logging console, and you can see that I'm getting a lot of MAC flaps in my network. And how a MAC flap is represented is you have the MAC address which is flapping, and it gives you the VLAN right here, and it tells you which ports it is flapping between. So in our situation, it says it's flapping between port gig 2/0/2 and port 2/0/3, right? So of course, it's good to understand what is a MAC flap. So layer 2 switches, or just switches in general, how they all work is something we all know. They're basically forwarding based on your layer 2 MAC addresses. The source MAC from incoming frames are mapped to the interface and the VLAN, and is stored in your CAM table, right? So for unicast MAC addresses, a MAC address can only be bound to one single interface. So what happens in the situation where the same switch gets another frame with the same source MAC address on a different interface? So as opposed to it learning, let's say on interface 2/0/2, now the switch is seeing the exact same frame. I'm sorry, let's not say exact. It's basically seeing a frame with the exact same source MAC address, but on a different interface. This constitutes a MAC flap. The MAC is said to have moved from one interface to the other interface. And this is very common in terms of a loop because packets are basically looping around. So the switches are seeing these packets coming in on one interface, and momentarily they see the same packets coming in on a different interface. And that's why you get a MAC flap. Of course, another way to see the MACs actually flapping is if you directly look at your MAC address table. You can just do an up arrow pretty quickly, and you should see the MACs flapping between the actual interfaces. So MAC flaps are a very, very obvious sign that you might have a loop in your network. Another thing to sort of focus on is your CPU being pegged? Because what happens when you have a loop in your network is, suppose there is an ARP that comes into this topology which is looped. Now, because ARP is a layer 2 broadcast, and because there's no concept of a time to live on layer 2 frames, these packets will never die. They will always loop around in a looped network forever until you actually physically or find a way to sort of shut down the loop. So now, because they're looping continuously, the number of packets increases exponentially based on the size of your network, and ARP is basically something that is CPU intensive. It has to be CPU processed. So these packets are continuously hitting your CPU, and you would see high CPU as well. So that is another way to sort of confirm if you're seeing a loop in your network or not. So if you see in our situation, I've gone, I didn't show you the actual output earlier, but I was sitting at about 5% CPU, and now I'm running at 99% CPU, and a lot of the packets, or a lot of the CPU is constituted by ARP input. So this is your second sign that sort of tells you, okay, I have a loop in my network, I have to do something about it. So the first thing that you want to do is, in this topology, it's very obvious where the loop is, but in your situations, the loop might be anywhere and your topologies will be very big. So what you need to do is, you need to concentrate on the interfaces where the MAC is flapping. So you find out how the interfaces are actually configured, right? Try and find out any sort of bad config on these interfaces. In our situation, it's very straightforward. They're simply trunk interfaces. So sitting on the switch, which is seeing the MAC flap, unfortunately, there's no easy way. You have to start building your layer 2 domain. You have to start drawing it out, you have to start writing it down, and you have to figure out what are my spanning tree states in my topology where I'm seeing the MAC flaps. So for the VLAN that we're seeing the MAC flap for, do a show spanning tree VLAN 1 and take special note on the interfaces that are involved in the MAC flap. So in our situation, we have gig 2/2 and we have 2/0/3. One is a designated port, one is a root port. That means both are forwarding traffic. What you do next is find out what is connected on these interfaces. You need to keep traversing switch by switch until you find the loop. So I have switch B on this interface, I have switch A on this interface. You go over to each of these switches, right? And look at the amount of MAC flaps that is being reported on this switch, right? So this is another indication. You go over to the other switch, you run your same command, enable MAC moves if it's not enabled, and then if you're seeing MAC moves, you know that this switch is also involved in your looped topology. So you do a spanning tree command, the exact same thing here again, and now we see the MAC is actually flapping between FA01 and FA02. Find out what spanning tree states are for these interfaces. It's again designated and it's a root port, so both are forwarding traffic. Find out where these interfaces are actually connected. So I see one goes to switch C, one goes to switch A. So at this point, what you're trying to do is you're building out your spanning tree states, you're drawing it out, you're writing it down, and once you do that, you'll realize that it's a triangle topology. Logically, I should have one interface which is blocked, but I don't. So now it sort of comes down to how quickly you want to recover, because such a loop in a large network it hurts a lot. It can bring down a lot of services, and you can see a major impact in your network. So sometimes as engineers, we might not have time to actually find out the root cause, but if you found out your loop topology, if you have the exact topology which is looped, and you know how spanning tree should have built itself, from this topology we know that the link between switch B and switch C should be blocking. As a quick measure, all you need to do is just quickly shut down the interface and bring the loop down, so that there's no loop, your services come back online, your CPU goes down, and then you can sort of try and understand why was there a loop in the first place. You can bring the interface back up in a maintenance window and do troubleshooting at that stage. So what I'm going to do is I will shut down the interface which connects to switch C. So that's interface FA0/1. And this should bring down your CPU as well. So look at that, in less than 5 seconds, we've got the CPU down to 12%, and it was 99% earlier. So you've successfully recovered from the loop. Now ensure that your network remains stable, nobody brings this link back up, you've isolated the problem, and let's try and understand what happens in a maintenance window. Because if you don't know why this link caused the loop and you bring it up again during your production, it'll just go into the same process again. Again, you're going to see an outage. And the outage, of course, in my situation is not very big, but in your situation, when you have CPU that is running at about 99%, you start dropping very important control packets such as your routing protocol control packets, EIGRP, OSPF, and all of that. You'll see HSRP flapping, you'll see your routing protocols flapping, and you'll see very, very critical services which are down. So it's important to understand that when you see a loop, sometimes you cannot find the root cause, or you don't have time to find the root cause at that point. So the first priority has to be restore services always, right? So and just to give you a simplified idea of how a loop presents itself, which is in terms of MAC moves and all of that, and how you can troubleshoot it and identify and finally fix the problem. So let's go back to the slide where we were. This was a stable topology. I introduced the loop, and we talked about what exactly are MAC moves. And this is just a sort of understanding of what a MAC move is and why it presents itself. So here you can see that the MAC address was learned in this fashion, and this is when everything was stable. Now that the loop has actually occurred, let's say I inject a single ARP into switch C. What switch C will do is it will send it to both switch A and send it to switch B. So now this is a situation where switch B has learned the MAC address from FA01, switch A has learned the MAC address from FA101. What will switch A do with this? It's an ARP, it has to flood out in the same VLAN, so it sends it out towards switch B. Now switch B is receiving the same ARP, or it's receiving an ARP with the exact same source MAC address. So previously the MAC address was learned on FA01, now I'm learning it on FA02. This constitutes a MAC move. So this is just the path of the frame that I've sort of explained, and then I'm learning it on FA02, and of course the switch realizes that the MAC just moved from interface FA01 to FA02 on VLAN 1, and it reports the exact same thing to you as a log. And this is sort of the log message that you get. It tells you the exact MAC address that is moving, which VLAN it is moving in, and which ports it is moving between. So you can see with a small topology, it's sort of easy to troubleshoot, but I think all of us can comprehend when you have a topology of 6-7 switches or even more, you are going to see some complexities arise out of the fact that you have to go into each switch, figure out what the spanning tree roles are and all of that, which is going to be time consuming, not just for you, it is going to be time consuming for a TAC engineer as well. We will have to follow the exact same process. There's no shortcut, there's no easy way of finding out where the loop is. So this is why TAC sort of insists and recommends that you should always have a topology in place with you beforehand. Even if you're not running into a situation which is bad for you, even if you have a stable network, you should always be prepared for a situation where you might have these conditions arise. So if you have a loop in your network and you basically open a TAC case and you give the topology to the TAC engineer, it is going to be very quick. We know where the switches are, we know the interfaces, we can run through the outputs very, very quickly. But if you don't give that to us, we're going to have to do it very, very slowly, do show CDP neighbor at every output, and that is time consuming. So this is just sort of to give you an understanding of how you can really make a difference as well, and how you can troubleshoot loops in your own network as well. So let's move on to the last topic from a spanning tree perspective. This is topology changes. So what is a topology change? What is a TCN? So a topology change notification is an indication of something that has changed in your network, right? There can be interfaces which are going up and down. There can be an interface which went down and a new path had to be recalculated to your route and all of that. Those sort of changes are signified or indicated by topology changes, right? So I wanted to explain this to you with the help of a diagram, and this should be quite interesting because this is a case that I handled some time back. So it is a case that TAC actually got and we had to troubleshoot, right? So this is something that you yourself can even troubleshoot. So the topology is fairly straightforward. It's a square topology. You have 4 switches. You can see they're numbered 6501, 6502, 4501, and 4502, right? Now the 6501, that has an interface VLAN 10 or the SVI for VLAN 10, and the 4502 has the SVI for VLAN 2. And I've signified the spanning tree port roles here. So the path, so in the situation when I'm pinging from 6501 to 4502 between the SVIs, the actual path that is taken for the packet is it goes down to 4501 and then it goes to 4502 because the other way is blocked. So if you can see 4501 interface 3/2, that is being blocked. So that path will never be taken for the actual data traffic. So we got the case. Basically, what was happening was the customer was testing certain failure conditions, and what they did was they wanted to unblock the blocked port. So we increased the cost of 4500.02 that is facing 4500.01, so that the previously blocked port, which is gig 3/2, becomes the root port, and the new path will be 6500.01, 6500.02, and then down to the 4500.02. So the customer did this, and what we saw was when we're pinging between the SVIs, our pings suddenly stop working. And this goes on for about roughly about 5 minutes, and the ping starts working again, right? So we come into the call, I come into the call, and we're trying to troubleshoot what is happening. So when such a change happens in your network, how does spanning tree react? How should it react? The first thing that happens is spanning tree should send a topology change notification. And why is that important? This example will show you why it is important. So what I found out was the reason that the 6500 was not able to ping the 4500 at the bottom was because the MAC address that was learned for that IP address was incorrectly learned. So I've given the output here. It says it's learned via gig 3/48. So going back to the diagram, where is gig 3/48? It goes down to 4500.01. So even when that specific path became blocked, 6500.01 was still trying to use that path because the MAC address was never updated. The MAC addresses were never flushed. The 6500 never knew the new path that it should use to go to 4500.02. And this is where TCN helps. This is why a topology change is so important. So when the 4500 moves its block port to a root port in this situation, it should generate a TCN which should reach 6500.01. 6500.01 should flush out the MAC address, and it should relearn the MAC address via the correct path. So this is what we found out. This is what the issue was. It became a different story from there, but this is the basic gist of why topology changes are really important for your network, right? MAC addresses have to be relearned from a new path if the path is changing. Of course, there's a sort of downside to it. Excessive TCNs are bad for your network as well, because TCNs cause constant flushing in your network, where if my switch receives a TCN based on the flavor of spanning tree I'm running, if it's PVST plus, I will reduce my MAC aging to 15 seconds and then flush the MAC address out. If it's rapid PVST plus, I will flush out the MAC address almost immediately. So you reach a situation where your MAC addresses are sort of constantly being flushed out, and of course if the switch gets a packet and the MAC address is not or no longer in its CAM table, what it does is it will unicast flood in that VLAN. So you see excessive flooding as a result of this. And of course, topology changes also indicate a lack of stability in your network, where interfaces are flapping or paths are constantly changing. So this is something that you sort of have to look into quickly and identify what is the reason for your topology change. So that is the next thing that I will address here. How do you identify what is the reason for your topology change? So topology changes can be seen via the show spanning tree detail command, and this gives you a lot of information, but what tag does is just to really quickly look at only the TCNs. We use this very handy command that I've listed down here, which is show spanning tree detail you include is exec occur from. So this will give you exactly how long ago a TCN was seen on the switch, which interface saw that TCN. So all you have to do is basically follow that interface, go to the other device, run the same command again and again till you identify what is the cause for your TCN, right? So let's do a quick 2-minute lab on this to trace down the TCN, and I'm going to use the same topology again. So just give me 1 quick minute. I'm going to bring the switches back up. All right, so I hope everyone can see the switches in question. I just want to go ahead and restore the previous functionality. So I'm going to go and remove the BPDU filter from the interface which I shut down. So this is the interface I had shut down previously. I want to remove the BPDU filter command. And I will no shut the interface and wait for a stable spanning tree topology to form. So if you look here, my interface has gone back to blocking. So I have now reached a stable spanning tree situation, right? So let's just wait for this interface to come to forwarding from learning, and then we can start testing. All right, so now it's come down to a forwarding state. Let's just ensure that switch A is still the root bridge. So we can see that here, this bridge is still the root. So let's do this. I have an interface connected here. So this is just an access interface in VLAN 1. Let's confirm that the interface is up. And you can see that line protocol and physically the interface is up. So what I want to do is let's make this interface flap and let's see how the TCNs are being generated. I'm just going to shut down the interface, right? So in PVST plus, even an interface which goes down will generate a TCN. So I go over to switch A, and of course it's not necessary to start from the root. You can start from any switch possible. So let's focus on VLAN 1, and I want the detail, and then let's run the include command as well, right? So it says I received a topology change for VLAN 1. I received it 27 seconds ago, and I saw the topology change on fast Ethernet 1/0/1. So of course we know why this happened. We know where fast Ethernet 101 connects to. But if you're not aware, or if you're in a situation where you don't know your topology, it's a very simple matter of simply following the interfaces. I've received it on this interface. Let's find out what this interface connects to. So it says this interface connects to switch C. You go over to switch C, you do the same command once more. You run the same command once more. I see it was received a minute back, and I see it was from 2/0/1. So you have to find out what exactly happened to 2/0/1. The first place to start is always the logs. So let's move down the MAC flaps, that's from the previous log, and look what happened here. Someone administratively shut down the interface. So we all know that was me, but if you're troubleshooting this in your environment, this is a sign that, okay, someone shut down this interface. I'm running PVST plus. When the interface goes down, that will generate a topology change, and I am seeing that on switch A, right? So this is how you would follow your topology changes. Simply run that command, find out which interface it was seen from, do a show CDP neighbor, find out what device is connected on that interface, move over to that device, and just repeat the exact same process again and again till you reach an interface that is flapping, or till you find out a spanning tree path that changed, right? Now, this is where I would like to bring in or come back to topology changes with respect to port fast. That is another handy feature of port fast, where if you have port fast configured on an interface, that does not generate a topology change. And that is good because port fast is basically used for workstation servers. And if my workstation is flapping, if the interface is flapping, I don't really need to inform the switch that my interface is flapping and the topology has changed, because from a layer 2 topology perspective, nothing has changed. Only the workstation interface is flapping. So I do not typically want a topology change generated in that situation. And this is particularly important in the situation where for some reason the interface is bad and it flaps excessively. You will see an excessive amount of TCNs which will be flushing out the MAC address for the entire VLAN. So that's kind of critical to understand. It doesn't flush out one MAC address, it flushes out MAC addresses for the entire VLAN, right? And you don't want that to happen just because a user workstation is flapping. You want to prevent that. This is why we always recommend and make sure that you have portfast configured on your end users. And if you don't have, go ahead and do that. That is important to have it there. So what I will do is on switch C, I'm going to configure portfast on this interface, make it flap again, and we'll see that the topology change is not generated. So I think I'm already under that interface. Let's just make sure. I'm going to do a spanning tree portfast command right here. Let's shut down this interface. And let's run through the same command again. And you see that nothing was generated. 4 minutes and 14 seconds back, we saw a topology change, but I just made the interface flap 5 seconds back, and there was nothing that changed. No topology change was generated, and this is why portfast is also important, right? So this should wrap up spanning tree as a whole, right? So we're going to move on to stacking, and Karthick is going to present that.
All right, thanks, Aninda. Good afternoon, guys. Myself, Karthick. I'm working as a TAC escalation engineer in LAN switching. Today, in this section, we are going to discuss about stack switches and what do we call, what are the technologies that we have in stack switches. And moving forward, we will also see about the features and the benefits of using stack switches. Okay. First of all, to start with, why we need a stack switch. Okay, if you consider Cisco platform, we have a higher end platform which are of kind of modular switches where you have a chassis and you have a supervisor and you have line cards which can function as a data plane, and the supervisor takes care of the control plane. So the Cisco wanted to get this feature implemented on a lower end platform which the lower end business can afford for. So that's when we brought in the concept of stacking. So what do we call a stack? There is a capability that we can connect more than 9 switches, okay, and not all switches can form a stack, okay. There are very specific set of switches that can form a stack, namely 3750, 3750X and 3750E. Any flavor of 3750 or most of the flavors of 3750 should support stack. Now, let's say you have two 3750 connected with the help of a proprietary cable called stack cable. Then those two switches will act like a single entity. When I say single entity, one of the switch will be considered as master. The other switch will act like a member, and any control plane traffic will be taken care by the master, and the data plane will be taken care by both the switches. Now, let's say we have a stack already in the network, and what all things we should remember, right? The first of all, whatever configuration you do on existing stack, it's going to be applicable, or everything will be pushed into the master switch, and a copy of running configuration or the MAC address table and the ARP table, everything will be in sync with the members. Now, with the existing stack, you can just remove one of the stack or one of the switches which is already working on the stack, or you can add one more switch to the existing stack, provided it's not exceeding more than 9 without impacting the performance or without interrupting the traffic. Okay, now when I say stack cable, when I say the proprietary cable that we use, right, how is it going to be of any use? When why can't we connect two switches with just an uplink or a 10 gig cable, which is going to again stack the switches? The difference is the stack cables has a greater capacity, which will more likely act like a fabric that we have on any higher end platform. When we take a 6500, we get a greater backplane speed. Why? Because we have a separate fabric from the supervisor to each and every module. Likewise, we brought in the concept of stack, which is going to serve you a 32 Gbps backplane speed, any communication from the supervisor or from the master switch to the slave or slave to the slave will be taken care or will be sent across the stack cable, which is going to give an improved performance for the switching network. Now let's discuss about the two types of stack protocol that we use. In olden days, the stack protocol that we used is called stackwise protocol. What is the meaning of stackwise, or how it is different from stackwise plus? Now, when we call stack, right, we have a stack cable which is connected on the rear side of the switch, which will look like a ring. Now, let's say you have 9 switches in the stack, and I'm going to transfer a packet from switch 1 to switch 9, right? Or switch 1 to switch 2 itself. Let's say switch 1 to switch 2 itself. Now, switch 1 is going to send the packet. How it's going to send the packet? It's going to put it on the ring. Now, as soon as it goes to the switch 2, where the actual destination is, the destination will take the packet out of the ring, and in stackwise technology, the packet will be still forward in the ring, and it will be stripped off from the ring only when it reaches the source who sends the packet. Whereas in this specific technology, the disadvantage is even for the directly connected switch, the traffic will have to go through the entire ring. So to overcome this, we got a concept called stackwise plus, which is currently in use. What's going to happen is it's going to let's consider the same scenario where the traffic is coming from the master and it goes to switch 2. As soon as it reaches the switch 2 where the destination is, it's going to strip off the packet from the ring, and the packet ends there itself. So in this way, we are going to save lots of bandwidth on the backplane. So this is the difference between the stackwise and the stackwise plus. Now, what are the important things that we need to worry about when you consider a stack as a single switch? So if you understand all these things, right, most of the troubleshooting will become easier when you are troubleshooting any kind of issues related to stack. Let's say you have a stack again with 3 switches connected with a stackwise cable. Now, when you log into any of the switches via console, let's say you log into the switch number 2 via console, you will still be in the CLI of switch 1 if switch 1 is a master. So irrespective of wherever you log in via console, the CLI will be taken care by the master itself. And they also have one VLAN database. Let's say you're getting a VLAN from a neighbor switch via VTP. It's going to be installed in the master switch, and which will be synced up with all the other slaves. And the entire switch will be considered as one STP node. Whereas if you consider connecting 2 switches with some uplink like a 10 gig cable, and if you are configuring STP on it, those 2 switches will act like 2 independent STP nodes. But whereas when you consider a stack switch, it's going to consider the entire 9 switches in the stack to be as a single STP node. And even routing table will be unique. And when you check CDP neighbor from the neighboring switch, it will show us one switch, which is going to be a stack switch. And whereas, how will you identify if it is going to switch 2 or switch 3 or switch 4? With the naming of the interface. Let's say when you do a show CDP neighbor from the switch, which is connected to switch 2, on the other end neighbor, you should see gig 2/0/1 of that sort. Now, we can club more than one type of stack switches. When I say more than one type, you can combine gig capable switch with fast Ethernet capable switch. They can interoperate with each other. Now, as we already told, the limitation is 9 switches in a stack. Now, okay, let's see about stack member numbers. So this is going to be one handy feature that you can have for better manageability. Apart from that, it might not be useful on a daily troubleshooting and things. Let's say you got a rack where you mounted the first switch in the first rack unit, and the second switch in the third rack unit, and the fourth switch in the fourth rack unit. And because you got a switch that goes into the rack unit in within 1 and 3, just for the better manageability, if you want to renumber the switch, you can renumber the switch at any point of time, but make sure whenever you do a renumber, you should also reload the switch for the new number to reflect on the switch. Okay, now let's see about how to change the number. Now there are two ways to do it. The first way is from the global configuration, from the privilege mode, you can just go ahead and change switch followed by the switch number and renumber keyword followed by the new number that you want to change. And once you do this, you have to save the configuration and you can reload it. Now there is one other way to do it. You can go break into the ROM1 by pressing the mode button on the 3750 switch, and you can set the number for it. So this probably one of the inconvenient method of doing it, but in case if you're already in ROM1, then you can do this using the command set switch underscore number followed by the number that you want to change. Okay, priority values. So this is one of the key element that we need to consider whenever we work on stack switches. Why we call it as a key element? Because in a stack switch, you have more than one switches in the stack, right? How do you define or how do you elect one specific switch as a master? So the first thing that will be considered for the master election will be the priority value. By default, all the switches will have the priority value of 1, and increasing the priority value to the max, it's going to give you the higher chances of becoming the master, and the max value being 15. Okay, now let's discuss about the stack master election process, because this is very, very critical, because deciding the master in the entire stack is one of the critical tasks. It might not make a difference if you have same kind of hardware version, same kind of iOS version. I mean, when I say iOS version, same kind of license versions, then it doesn't matter. We can bring up any switch as a master. But consider a scenario, you have a 3750X, which doesn't allow you to upgrade the feature like the IP services or IP base just like that. We need to purchase a license and we need to unlock the feature, right? So whenever we do that, let's say you have a stack switch of 9 members and your company has got a budget to buy only one license, right? In that case, what you can do is you can buy a IP services license and you can unlock the feature on one of the switch, right? And you can set the priority for the switch to be higher, let's say 15. And once you reload the entire switch with the highest priority value, it's going to come up, and once it is up, all the switches in the stack will also have the behavior of IP services, although we do not have the license unlocked or the feature unlocked for the other switches. So, but this will be a problem in case if your master is going to fail, your IP features is going to be disabled, and the second master, if the switch doesn't have that IP services license, then it will fall back to the original behavior that you had or the original feature you had. Let's say LAN base, then it will fall back to LAN base, which might cause unexpected outage. So that you need to remember. Okay, let's concentrate on stack master election process. So you have a stack of 9 members, let's say. What all things will be considered for the master election? First of all, it's going to check for the highest stack member with the highest priority value, and that will be elected as the master. Second, let's say you have 2 switch in the stack and both of them are having same priority value. Then what's going to be the tiebreaker? Let's say in switch 1 you have some kind of configuration, and in switch 2 you do not have anything at all. The chances of becoming switch 1 be the master is more, because the switch 2 doesn't have any configuration. So the stack is going to believe that the other guy is in the network for a long time, and it's going to bring up that switch as a master. The third one, the hardware priority and the software priority. So hardware priority is nothing but the version of switch that we run. Let's say 3750 V2 versus 3750 V1. It will consider 3750 version 2 to be higher, and that will be selected. Now, image type. Let's say you have three switches, where you have in one switch you have IP services K9, which is nothing but the cryptographic image. The other one has just the IP services without any K9 images, just the IP services image. And the third one has an IP-based image with the K9 feature. So in that case, when it is booting up, it will always give priority to the IP services. Out of IP services, it's going to check who has the K9 image, and it will select that specific switch as the master. This will come into picture only if the other criteria aren't high. If all these features or if all these things are common or same, it's going to look at the highest uptime. When I say the highest uptime, let's say you boot one switch. After 3 minutes, you are going to boot up the second switch. The greater the chance of becoming the master for the first switch is more. Even if the uptime is going to be same, most of the time it might not be same, but in case if it's going to be same, then it's going to look at the lowest MAC address of the switch, and that specific switch will become the master. In the existing stack, if you're going to add a new switch, and if the new switch is going to undergo an election process, it's not going to impact any of the data forwarding that's actually happening on the stack switch. All right. So when our stack master election will happen, let's say if the entire switch reloads, yes, obviously it's going to search for the master who's going to take the role of the control plane. And if the existing master goes down, then it's going to do the master election to identify the second capable master. Let's say if the master is removed from the stack, again it's going to be the same scenario as the stack master is being reset, and it's going to undergo the election process again. Even in the failure of master, it's going to be the same case. Let's say in the fifth step that I'm going to talk might not be common always, but it's seen in most of the cases where you have an existing stack and you're adding a stack to an existing, adding a switch to an existing stack. It's not going to impact anything unless it is powered down. If you're going to add a switch powered on to the existing stack with the higher priority, it's going to reinforce the election process, which might bring down the entire stack. So caution, please power down the switch before you add to the existing stack. Now, how do we compare the software compatibility? So now, this is one important criteria that you need to consider whenever you add a switch into the existing stack. Let's say your existing stack is running a version of code 12.255 AC5, right? And you're going to add another switch, which is 15.0 XX. Now, what's going to happen, right? Whenever you add a new switch to the existing stack, this platform stack manager is the manager is going to see if the newly added switch is capable of understanding whatever the existing switch is performing. And if there is a mismatch in the major version, when I say major version, the existing stack has got 12.2 55 AC5, where 12.2 is the major version, and 15.0 AC5 in 15.0 is the major version. If there is a difference, in the major version, then it's not going to combine that specific switch into the existing stack. So, but in case if you are adding a switch into the existing stack, let's say you have a version called 12.2 58 AC5 to the existing stack, which has 12.2 55 AC5. There is a mismatch in the minor version, 55 versus 58. In that case, they can form a partial stack, and it would throw up a message saying version mismatch. When there is a version mismatch, what's going to happen is the slave switch is going to request for the code that we have on the existing stack, and which is going to upgrade the slave switch by itself, and it will try to add up to the existing stack. This is not always seen, but if you had used a tar image to upgrade your existing stack, then the download of image from the existing stack to the newly added switch is always possible. Now, what are things the master switch performs? The master switch acts as a primary point for the CLI that we already told. Whenever you do a telnet or SSH, it's going to be the same it's going to be handled by the master switch. And any fib or when I say fib, the forward information base or the routing table will be updated by the master switch to the other switches. And whenever you add up a new switch, the notification and everything will be sent by the master switch. Now, it is also the responsibility of the master switch to update the MAC addresses of all the switches in the stack, and it updates the MAC addresses or pushes the MAC address that it learned from the other switches to other slaves. The member switches, it maintains two tables. One is the local MAC address table, and the other one is the MAC address table of its own. Now, let's consider one last scenario in stack, which is a commonly seen scenario. Let's say you have two stack. One stack has three switches, A1, A2, A3, and the other stack has B1, B2, B3. Right? If you're going to merge these two stacks together, what's going to happen? Let's say now A1 is the master of the A stack, and B1 is the master of the B stack. When you're going to merge these two stacks, right, again the election is going to happen, and let's say if A1 is going to win the race, A1 is elected as a master, all the configuration on B1, B2, B3 will be wiped out, and the configuration from A1, A2, A3 or from A1 will be copied to B1, B2, B3. Also, the number that we had on the B stack, like 1, 2, 3, will be renumbered as 4, 5, 6. This is one of the common scenarios we had seen in our experience, so this might be useful during your troubleshooting. The configuration management is going to be the same thing, where whenever you do a configuration on your master, which will be pushed to the slaves in the stack. And the slave also keeps a copy of the startup and the running configuration always. So in case of master failure, it's going to bring up the slave can become the master, and it can take care of forwarding the traffic seamlessly. That's it about the stack management. So there are few useful commands that I will be showing now on the console, and after that we will also discuss about a few QoS parameters. Okay, let me just bring up the console. All right, so this is an existing stack, and I have 3 members. How do we know how many members we have on this stack? This is a command which will help you to identify the number of members in the existing stack. How do we know the priority set for each and every stack switch? You can find with the same command, and you have an option to change the switch priority with the help of this command. And you can confirm the priority is taken with the same command. Now, let's say you have the stacks connected and you are monitoring or managing the switch remotely. How do we know the stack cables are connected? So this is one command that will be of use. Let's say, so this is how the ports are connected. Now, switch 1, stack port 1 is connected to switch 3, port 1. And similarly, port 2 of switch 1 is connected to port 2 of switch 2. Now, let's say there is a performance issues in the existing stack. The traffic coming from switch 1 to switch 2 is severely degraded. How do we know if there are any issues with the stack port? So this command will help you. Okay, so this is one handy command that everyone should be aware of. Now, whenever there is a flap or whenever there is some issues with one of the ports of the stack, right? So let's say this is 1/1, which means stack port 1 of switch 1, stack port 2 of switch 1. So if there are any changes here, which is going to affect the performance of the stack as a whole, because any packet from one switch to the other switch goes via the stack ring. Apart from that, you can also execute this command. Right, you have all these options. You can check this, which is going to tell you if there are any activities happening. So although it might not make sense for if you read it as zeros and zeros, but they're definitely going to tell you if there are any activities happening. So this will be mostly used by the tag engineers during troubleshooting. Now, these are the things that you need to take care of while you're troubleshooting stacks. Now, I'm going to talk about a few QoS parameters and things, right? So I'm not going to touch upon the basic features like queuing or shaping or policing and things, but I'm going to talk about the major concern that we always have during the implementation of QoS. Most of the time, we'll never have issues in marking the traffic, but to preserve the marking throughout the path is always a challenge, right? So now I'm going to show a scenario where a traffic from node A to node B, let's say that's a EF traffic, which is a priority traffic going across a stack switch. How can we preserve this? So I have a scenario here. Let's say show IP in brief here. I have 10.10.10.1, which is in VLAN 10, and here I have 10.10.10.1.1.3. So let's say I'm going to send a traffic from this guy. Let's say this is an IP phone for the sake of troubleshooting, right? Let's say this is an IP phone which is sending a traffic to one of the call manager. Let's say there is a server located on the remote end, right? And I'm sending an EF traffic. How can I simulate an EF traffic? I'm just setting a the task bit, which is an equivalent version of DSCP for EF. Okay, I'm sending this traffic out here. See, we have sent 100 packets to the other end, and it is a successful packet, right? Now, how do we know if the packets are getting marked, and how do we know if while it is going out, it is still preserved? This is one of the important commands that everyone should aware when you are troubleshooting anything related to QoS. Let's say now, which is the port that goes to node A? Gig 2/0/2, right? Show MLS QoS interface gig 202 statistics. Okay, let me clear this so that we know what is the current flow here. So this is a command to clear the existing statistics. Clear MLS QoS interface statistics. Now let me initiate the ping again. Okay, I've already sent the traffic. Let me see. Okay, I'm checking it on MLS QoS interface gig 20 statistics. Okay, we see a EF traffic which carries a DSCP value of 46 sitting in here. However, this is the egress port that goes to the other node. Let's say show MLS QoS interface gig 201 statistics. You see the DSCP value or the marking that we had from the other interface has been stripped off. So this is a default behavior. So this you need to understand. Whenever there is a traffic coming in on a L2 port, by default whatever marking you have on the packet will be stripped off until and unless you trust that specific port. So now I'm going to show you a scenario. See, in this I'm going to trust the DSCP, let's say, which is the port that goes to the node A, which is gig 202, right? I'm going to enable the trust on this, right? Now let me initiate the traffic again. Before that, let me again clear the statistics. Okay, let me initiate the traffic again. Okay, again I've sent 100 packets. Let me see, show MLS where's interface gig 202 statistics. We again see the packets are coming in on DSCP 46. Let me also see now to the interface that goes to the node B. show MLS QoS interface gig 201 statistics. You see here, the DHCP value is preserved. So this is very critical because let's say your voice traffic is coming in via the access port. Until and unless you trust the DHCP value, it's not going to be preserved until it reaches the actual destination phone or the actual destination server. So this is one scenario that you need to worry about and you need to take care. We always wanted to cover upon all the platform where we wanted to show you a live demo on all the 6500 and 4500 platform, and because of restrictions of time and things, we are not able to cover everything on the same section, but probably we'll be doing the same thing in the future.